All right, we are group 24. I'm Qiyuan.
I'm Joe.
I'm Allison.
Okay, we are going to present our project Uncertainty-Aware Reinforcement Learning for Autonomous Driving. The intuition for the insight for this project is that in driving scenes, human drivers predict surrounding agents' future trajectories or behaviors in their mind to help planning ego trajectory. But the future behaviors of the surrounding agents and the ego are highly uncertain and inherently to be multimodal. So our hypothesis here is modeling uncertainty in agents' future behavior lead to safer and more robust decision making.
For the overview approach, our approach was divided into three parts. For the simulation environment, we are using the color simulator. And for the motion predictor, we are using QCNet as a model-based policies. And for policy learner, we're using PPO, which is a model-free. And so we set baseline for our project. So the baseline for the QCNet was there's no predicted motion. So basically, then it will turn the project into a model free learning. But in our test case, we did predict the motion, which means we use the QCNet. For the PPO, our baseline was just trained with the current state observation. And in the test case, we did train with future predicted future trajectory, which are from the QC nets.
To train and evaluate our self-driving agent under uncertainty, we built a modular and configurable simulation environment using Carla. Our setup allows us to simulate realistic driving conditions, including traffic, pedestrians, and varying weather like rain or sunset glare. We made simulation reproducible by setting random seeds and running in synchronous mode, which ensures consistent environment steps across training runs. And this control is crucial for debugging and for comparing models under identical scenarios. We also supported scenario customization through map and pedestrian selection. This infrastructure not only helped us prototype faster, but enabled testing in rare or high risk edge cases, something real world testing just can't do reliably or safely.
The motion predictor we use here is QCNet, which is a state-of-the-art transformer-based trajectory prediction framework. It intakes the map information alongside with all agents' state histories and output the predicted trajectories, predicted future trajectories for all agents. So in our framework, we randomly sample one future trajectory as a part of our observation, the ego vehicle's observation to help ego vehicle's decision making.
Sorry, for the PPO, as we mentioned above, we are using we're using PPO as our RL algorithm, and it's MLP policies. And for observation space, it includes ego and surrounding agents, including vehicles and pedestrians, states, and of course optional QC predictions. And for action space, there's only two which control the car, which is throttle and steering. And for rewards, we need the car to drive safely and fast as possible and without any collision or to manage steering because that's what a good driver would do. And I provided two pictures about the reward functions in the next slide. And as you can see, there's like eight consideration or eight variables we took into the considerations, and the weight for collision and the weight for the collision is really heavy, and because we want the car to avoid collision possibly, and we want the car to reach the goals. Yeah.
Okay, here's our takeaways. So for me, this project given strong impression that reinforcement learning, even simple algorithms such as the PPO we use here, it's much harder to train than I previously thought. I spent quite some effort like building up the pipeline and tuning the reward weights, learning rates. RL, it's like a complex engineering system to me that we need each part of them to work properly and just combine them all together into a complexity.
And for me, communication is really important, especially like in our project, which I need to coordinate the integration between PPO, QCNet, and the car simulator. So it requires me to like do some frequent and efficiency communication, which that's the most important takeaway for me.
The most important takeaway for me was that uncertainty modeling really helped our agent perform better in unpredictable settings. When we trained it in Carla, we didn't just show it clean, ideal driving. We dropped it into messy traffic. We gave it surprise pedestrians. We didn't just make it simple, we made it realistic. By doing that, the agent learned to be more cautious, to think ahead, and to make smart decisions in situations that aren't always black and white. And that kind of behavior is exactly what you want from a system that needs to operate safely in the real world.